This video has been sponsored by Nuage Networks. For more information on the Nuage Virtualized Services platform and how Nuage is delivering consistent policy-driven automation across data centers, the WAN, and branch locations everywhere, please visit nuagenetworks.net and follow us on Twitter at Nuage Networks. We hope you enjoy the session.
After watching this video, visit ipspace.net/SDN to learn more about software-defined networking and overlay virtual networks. Most overlay virtual networks today are implemented with some sort of controller. Initial VXLAN implementations used IP multicast and Ethernet-like learning. Today, almost everyone is using some sort of network controller in combination with the orchestration system. Some overlay virtual networking solutions don't have an SDN controller. So the question is, well, do we need one? After all, Microsoft doesn't have it in Hyper-V. In that case, the Microsoft System Center configures the virtual switches directly. For an isolated environment, that's perfectly good enough. But if you want to integrate this environment with the physical network, then there's always the question of, well, who will provide the connectivity to the physical network and who will be the single source of truth about the reachability information inside the cloud and the physical network. The cloud management system is the single source of truth for in-cloud reachability information. After all, it knows where the VMs are, what IP and MAC addresses they use, but it doesn't know about the external world. And this is where we need this link between an SDN controller, whether it's integrated with the cloud management platform or not is a different story, and the external world. And over this control plane connection, the SDN controller exchanges reachability information with the outside world. Obviously, the other solution is you use static routes like Hyper-V is using. And even when they run BGP with the outside world inside the virtual tenant network, they still use a default route toward the gateway. Anyway, most SDN controllers on the market today use BGP if they have some federation capabilities, because the existing hardware, the existing PE routers use BGP, so it's very simple to connect to them if you use a protocol that they already support. Now, regardless of how well you build your controller, regardless of all the scalability features that you build into it, there will be a point where your controller will become the scalability bottleneck. I will not mention any products, but if you just go around and read the release notes from different implementations, you will see that it ranges from a few tens to a few hundreds or maybe 1,000 to 3,000 hosts per controller cluster. By the way, the controllers that stay away from the data plane, so the controllers that don't reply to ARP requests, for example, scale better than the controllers that have to deal with data plane activities like ARP requests. But every controller implementation will eventually hit the limits, and in that case, scale out is the only answer. This is, for example, what you could do. You build clusters of controller. Well, you would have one or more controllers in a cluster for resilience. And this controller would control a reasonable number of virtual switches for whatever value of reasonable. And then you would build a different cluster of controller and associated virtual switches and run something between them. That something could in principle be anything. If you love MongoDB, why not? It would do. If you run any other key value store, sure, go for it. But most implementations choose something that has been tested in large-scale real-life networks like Internet or large-scale MPLS VPN implementations. So you'll see that most of these scale-out architectures use multi-protocol BGP. If they are based primarily on layer 3 forwarding, you would see them using layer 3 VPNs, and sometimes even for implementations that are more focused toward layer 2 or a combination of layer 2 and layer 3, you would see them use host routes for VM IP addresses and pass those host routes in multi-protocol BGP so that you retain the nice properties of VM mobility. For pure layer 2 forwarding, more or less everyone is using EVPN. And if you use this too, then it's pretty easy to integrate with the existing hardware gateways. For example, if your solution is using layer 3 VPN, the traditional MPLS VPN stuff, it's easy to integrate with existing PE routers, be it from Cisco, Juniper, Nuage, Alcatel, Lucent, or anyone else. An additional benefit of a scale-out architecture is that you have clear failure domains, or if you want to call them, availability zones. So you have one failure domain here. If this controller fails, you lose all this, but nothing more. You have a different, totally independent failure domain there. But we'll talk more about failure domains in a few minutes. Also, it's possible to adjust, if you have a scale-out architecture, the ratio of controller to hosts. So maybe you want to have small availability zones or failure domains so that if the controller crashes, you only lose a few tens of hosts. Or maybe you want to keep things simpler and you have one controller per 100 or hundreds of hosts. And also it depends on how quickly things change in your environment. If you have pretty static environment, or if your convergence requirements are measured in seconds, then you can afford to have one controller for many hosts. If, for example, you're running Docker environment where there are not only VMs going up and down, but Docker containers going up and down every second, then obviously you need a different ratio of controllers to hosts. Nuage, for example, has an interesting architecture where obviously on the top you have the cloud management platform, and then you would have the policy engine called Virtual Services Directory. The policy engine would be more or less centralized and co-resident with the cloud management platform. But the network controllers called Virtual Services Controllers can be spread out and they talk and exchange reachability information through BGP. On the other hand, when you, for example, provision a new tenant, or when a new tenant starts the first VM on some virtual services controller, then the request has to go all the way up to the virtual services directory server. Here they use XMPP as the control protocol, and then VSD would download the policy data to VSC, which then instantiates the forwarding policy in the virtual routing and switching, the vSwitch in every hypervisor. So you would have usually single VSD per cloud management platform, and then you would have multiple VSCs per VSD and cloud management platform. And you can have a confederation or federation, whatever you want to call it, of VSCs within one instance of cloud management platform or even across multiple instances. And if you wish, even with the outside world. How would you integrate SDN-based cloud if you have multiple locations? One central big SDN controller or multiple controllers which are all redundant? I would go for multiple controllers. In the worst case, I would have one controller cluster per location. In the ideal case, I will have multiple controller clusters on each location, as I'll explain in a minute in the availability zones section. Is it okay for cloud management system to program data plane entry? As the cloud management system would typically run in out-of-band network, they may not have idea of data plane connectivity. That is absolutely true. That aspect is, let's be honest, usually ignored. There are some solutions that actually test connectivity between different hypervisors and then act on potential lack of connectivity. But in many cases, the idea is, well, we'll treat the underlay transport network as a cloud. And we have 2 uplinks from every hypervisor host to this double quotes cloud. So this is the transport network. And we assume that the transport network is doing its job. So it's a clear separation of responsibilities. The transport network should provide end-to-end connectivity. And the hypervisors and the overlay virtual networks rely on the transport network providing the connectivity. It's like, in voice over IP systems, typical voice over IP client is not concerned about the way the internet will provide connectivity to the other client. The connectivity has to be there. There is nothing a voice over IP client would do to find another path or something. Obviously, voice gateways and session border controllers are a different story, but let's not go there.
Even if I may add something here, an interesting thing is that, for example, what we do here is that the VSC, the controller, actually peers with the underlay as a listener and understands the topology of the underlay. So provided you have a layer 3 underlay, if there is no route from one hypervisor to the other, then by implementing next hop tracking, we can withdraw the routes and obviously raise an alarm and know about it. So that's one aspect of the underlay integration. And the other aspect is by communicating between the controllers and the hypervisors in band. When you lose connectivity between the controllers and hypervisors, then the controller is immediately alarmed. So if you lose the top of rack switch, for example, then the controller will immediately know about it and can take the proper action after that.
Absolutely. Thank you for pointing that out. So we have 2 options, either shared fate, when the out-of-band control plane network is sharing the same physical links as the transport network. So if there is a link error, we know that we have a connectivity problem. And second one, by listening to the routers in the transport network and extracting the topology information from, oh, by the way, Dimitri, do you use BGP for that, or can you also use OSPF or ISIS?
We can use any IGP that is available, so all of them.
So VSC becomes a regular router in the transport network, and then it uses the regular BGP next hop handling mechanism in BGP route selection process.
That's correct.
Perfect. Thank you for pointing this out. And the final one, and then we move forward. What do you feel about the impact of app tunnels, basically apps being self-sufficient on native SSL VPN for connectivity? So what will be the impact of those solutions on the need for this type of robust network virtual infrastructure support moving forward? There are 2 aspects to this. First, yes, there are applications that are capable of doing that. They are few and far between. I don't expect that to be a major deployment model anytime soon. Maybe for startups, but definitely not in more traditional enterprise workloads. And on the other hand, even if you have something like this, some people still want to have their own isolated network for whatever security reasons. Yet again, I wouldn't expect that from startups, but more traditional enterprises would definitely want to have their own more private environment. After all, that's why Amazon had to implement VPC to get more traditional workloads onto Amazon. If you like this video, go to ipspace.net/cloud to explore other overlay virtual networking webinars.